Hooke's law, Robert Hooke said that stress is directly proportional to strain, but this law is subject to the limit, that is within elastic limit. In fact, within elastic limit, this law is not applicable. Now, it should be clear. It is proportional up to the limit of proportionality only. When we plot the graph, the proportionality continues up to a point, but elasticity continues even beyond that. So, Hooke's law is not applicable up to the elastic limit. It is proportional, means stress and strain are proportional up to the limit of proportionality only. When you plot the graph, this is a straight line. The ratio is known as modulus of elasticity. Remember, the reciprocal of modulus of elasticity is known as deformability. 1 upon E, that would be known as deformability. Depending on the deformation, modulus will also be of 3 types. Obviously, when you consider torsional change in deformation, it's going to be of 4 types. Here we'll focus on 3: Young's modulus, bulk and shear modulus. Young's modulus is related with longitudinal stress. The stress upon strain ratio would be Young's modulus. Values you know already, F upon A, delta L by L. This is going to be Young's modulus. Young's modulus could be defined only where the length could be defined. Then Young's modulus cannot be relevant for liquids and gases. It's applicable only to solids. Bulk modulus deals with the change in volume, volumetric stress, volumetric strain. The ratio you'll find P, delta P, that I told you, normal stress is equal to delta P, volumetric strain ratio is going to be bulk modulus. Bulk modulus delta P upon delta V upon V. You have already calculated the value of tangential stress and shearing strain. If you take the ratio, you will find modulus of rigidity F upon A theta. Then Poisson's ratio beta upon alpha, that is Poisson's ratio, lateral strain and primary strain. Primary strain means you first change the length of the wire, then it is followed by the change in radius. That's why the nomenclature primary and secondary. It's also known as longitudinal and lateral. This is known as lateral strain. This is known as longitudinal strain. If the material is perfectly incompressible, then it's going to be 0.5. But normally we find its value lies between 0 and 0.5. For cork and for rubber, the values have been given separately. Now, let's start from force and extension. You see, the deforming force greater, deformation will also be greater. That means the two are proportional. If you plot the graph between force and extension up to the limit of proportionality, it's going to be straight line. The area, this is going to be work done. When you say force is proportional to extension, you divide it by area, you divide it by length. This is stress, this is a strain. Stress is proportional to strain. This again is going to be a straight line. This area will be equal to work done per unit volume. Work done per unit volume, this is half stress into strain. The work that is done against the intermolecular forces in the process of deformation is stored as potential energy, that's known as elastic potential energy. Elastic potential energy, this work done is converted into elastic potential energy. This energy per unit volume will be equal to half stress into strain. Now it could be changed by multiplying it strain. In the numerator and denominator, if we multiply by strain, we will find strain square. And if we multiply by stress in numerator and denominator, it will be stress square. This is important result, that elastic potential energy per unit volume, this depends on stress square, also depends on strain square as well. The values for steel, copper, aluminum have been given for Young's modulus, bulk modulus, shear modulus for your ready reference. You can refer through all.